And hello friends, welcome back to this video. The last video I actually showed you a little bit of bits of code. Yeah, so basically last time I was talking about how to get from the complex gain data, or not exactly called complex gain, the frequency response data, when all the frequency response is in a complex number form, how you turn that into a transfer function. Okay. The only thing was this, of course, there was some funny shape plots, okay? And the code was a little bit messed up. And the code was a bit messed up, and you know, this part here is not very symmetrical. In fact, you're supposed, I think, in the data, we are actually going all the way to 20 Hertz, right? The sampling frequency is actually, technically speaking, 20 Hertz, but somehow things are a little bit off. Why is that the case? Okay, well, of course you can do without the right hand side mirror, because the left hand side will kind of take in everything. Okay, so let's walk through before we talk more about transfer function. I mean, if you want to go for transfer function stuff, just skip ahead at least this portion. So maybe it's in this video towards the end, or maybe a few videos ahead. I cannot plan. I'm not going to plan. I'm just going to take it as it comes. Okay. So why is the Fourier transform behaving so weird? Okay. So the one reason is this. Okay. Okay. So normally we get our sampling frequency. Okay. First, when we do our Fourier transform, we actually convert the CSV into an array, so that one doesn't really need too much explanation. You can go and take a look at the code. But here's where a lot of the things happen. Okay, so first thing I measure is the length, which is the number of data points. Okay, second thing I measure is the delta t, which is the time from the last point to the first point. So if you were to see this, okay, let's calculate delta t manually, and that's equals to frequency data, okay, the last, okay, how do you say, let's see, okay, maybe I'll do it a bit more manually like this. Okay, so let's look at frequency data. We'll look at the last time step. Oh, not the frequency data, the input data. Yeah. Oh, all right. This is the non-Fourier transform version. So I have to look at this data. Yes. Okay. So my last number is this 384, and so let's keep that in mind, 384. And my first number is 384. My last number is 20352. So let's look. 203. Oh, let's try again. 20352 minus 384. Okay. Then you have this being your delta t. Now, if you try to divide it by how many you try to get your sampling frequency, fs. Okay, your sampling frequency will be n, which is the number of data points. So that's 397152 data points. Okay, fs equals 397152 divided by delta t. All right. So you can see, okay, this the sampling frequency that is estimated is around 19.8894 Hertz, which is pretty close to the original input of 20 Hertz. Okay, very close. Okay, but it's not close enough because in fact from 19.889 all the way up to 20, the thing is you kind of just miss out. You miss out your you kind of just do away with all the data on the right hand side. Okay, so how did the code work? Okay, so what this code will say is that we will we will do a non-uniform fast Fourier transform, and then we will perform those Fourier transforms at certain frequencies. So those frequencies will go from 0 Hz all the way up to the sampling frequency. In this case, 19.8894 Hz. Okay, this is not 20 Hz. Okay. The reason why, the reason why this funny bug actually happens is because when I generated this data using LabVIEW, I intended for data to be taken in every 50 milliseconds. So I intended for data to be sampled every 50 milliseconds. Right? Data will be sampled every 50 milliseconds. However, LabVIEW will have some execution time. So maybe there will be another 0.3 milliseconds of calculation. So what happens is that every time you sample, you actually have 50.3 milliseconds. Okay, and let me show you how I got the number. Okay, so this is the sampling frequency. Okay, so what is your sampling interval? Okay, let's put sampling frequency. Okay, so what's your sampling interval? Sampling interval is actually fs divided by n. So let's do fs, or rather, oh no, I'm not doing fs divided by n, sorry. Let's take a look again. My FFT. Okay, let me start again. Okay, so I'm trying to we'll have a frequency we'll have a frequency vector of frequencies that we want to perform our Fourier transforms at, and the maximum frequency here is 19.8894. Okay, that is based on this 397,152 over delta t. Okay, so if I take 1 over fs, okay, sampling interval equals 1 over fs. Okay, you can see the sampling interval is 0.0503. Okay, if I take 1 divided by 0.0503, you will get back your sampling frequency. But if I take 1 divided by 0.05, which is what I originally intended, okay, then what I will have is I will have about 20 Hz. 1 over 0.05 is 20 Hz. So, okay, 1 divided by 0.0. Oh wait, I can do it in MATLAB. What am I doing? 1 divided by 0.05. That's 20 Hz. As compared to 1 divided by 0.0503. That's 19.8894. So, okay, so there is this issue where you don't capture the whole spectrum, because at least for LabVIEW, when I was generating this data, I did not so-called factor in this calculation time when I'm trying to consider this sampling frequency. Okay, so so there is a little bit of this out of sync, the time being out of sync, but no worries, we still actually have all our data, and we actually have all our data here, no problem. Okay, it's just when you want to find your Nyquist frequency, okay, we roughly know it's around 10 Hz, because that's how, because 20 Hz was the original sampling frequency. But from this graph, you can also tell the sampling frequency is around 10 Hz, because this is where like the axis of symmetry is supposed to be. Okay, so the only thing here is we want to supply the Nyquist frequency when we start to develop the IDFRD data. Alright, and that's in over here, where I have my transfer function script, and I convert this thing to a IDFRD data. Okay, now the reason why I kind of separated these two scripts, the Fourier transform script and the transfer function script, is because, for example, if I were to use one sine wave at one frequency at every to do frequency response, then I will have to take several frequency response data and then copy and paste it into a CSV file. Okay, then the transfer function has to be plotted using multiple tests. Okay, but if you are only using one test to test various frequencies, you don't need to slowly copy and paste so many frequencies over. All the frequency data is completed within one test. So that's a good thing about, of course, this pseudo random input. Okay, so probably what I want to do is now well, we have one workaround is to actually supply a so-called list of frequencies, and then you get the maximum. Okay, you get the maximum. Yeah, you kind of get the maximum frequency. Okay, you get the maximum frequency, and then after that you take that to be your so-called sampling frequency. Then you divide it by half, then you roughly get your Nyquist frequency. Okay, so that's one workaround, but it kind of takes a lot of manual work. So now probably what I want to do is code something a little bit newer. So at least you understand, as I code live before you understand how the script works. Okay, so I'm going to code another script. Okay, so what this script will do is that it will perform the non-uniform fast Fourier transform and then simultaneously convert it into frequency response data. Okay, so I'll put this last part will be convert frequency data into, or peak data into frequency response data. Okay, so peak data, I kind of explained how this was gotten before. Okay, I explained how this was gotten before, all this peak data thing. Okay, so now well, the next thing here is to just try to convert it into a IDFRD code. Convert all of this into IDFRD. All my frequency response data, I need to convert it into IDFRD. Okay, so next thing, what I want to do is look at this peak data. Okay, I have my input peak magnitude, my input peak frequencies, output peak magnitude, output peak frequencies, and I have my peak frequencies and complex gain. Okay, so all of this is inside this peak data object, but I want to add one more object first. Okay, I want to add this frequency data in so I can get my Nyquist frequency. Okay, so what do I do? Okay, I'm going to add Nyquist frequency into peak data. So Nyquist. Okay, let's see. Okay, so wait, I'm not going to add Nyquist frequency directly though. I'm kind of skipping ahead of myself, but okay, I'll just add the Nyquist frequency into the peak data. Okay, so sampling frequency. Okay, sampling frequency. Oh wait, no. Peak data dot sampling frequency hertz equals to what? Max of f. Okay, make sense? Cause what this f over here is all your frequency data, and the sampling one will, the best estimate for sampling at the moment is your this number over here, the maximum frequency over here. Okay, and next thing I'll have peak data dot what do I want? Nyquist. So I'm just going to put all the frequencies in there. Frequency equals to max f over 2. Okay, that's the Nyquist frequency. So that's the maximum, that's the sampling frequency over 2. And of course peak data dot sampling, okay, sampling interval. So this frequency will be in hertz. Sampling interval in seconds. Okay, what will it be? It will be the 1 divided by the sampling frequency, 1 over max f. Okay, so this code's a bit inefficient. Of course, I can actually just copy this and paste here. Alright, and actually that will be way more efficient, so I don't have to use the maximum function so many times. So let's press play and see whether this works. Okay. Okay, so it has an unrecognized field name, sampling frequency. Okay. Well, looks like I have this. Oh, sampling frequency hertz is supposed to be the thing. Okay, so let's do sampling frequency hertz. Okay, let's do it again. And everything should be, it's just a syntax error. Okay. So now you see that the peak data here will have sampling frequency hertz, Nyquist frequency hertz, and sampling interval in seconds. Okay, so now all of this data is available for us to perform a fast Fourier transform. So not fast Fourier transform, transfer function estimation. So let me convert to IDFRD. I'll have a function here, and that function I will just copy and paste from the transfer function. Whatever I have already. Excuse me. Okay, so function something to IDFRD. Okay, so I won't have CSV to IDFRD. So excuse me, I won't have CSV to IDFRD, but what I'll have is just have two arrays, and then I'll load it into the IDFRD frequency response data kind of an object. So let's do peak data to IDFRD. Okay, and my input will only be peak data. My input will only be peak data. Alright, so alright, I'm going to load in the sampling frequency first. Okay, so all of this is just to convert into a IDFRD object. So I load in the sampling frequency first, my sampling or my sampling time, my sampling sampling interval. Okay, my sampling interval is equals to peak data dot sampling interval. Okay, peak data sampling interval seconds. Okay, I'm also going to copy and paste this whole name here. Alright. Okay, so this will be my sampling interval. Okay, so originally I was going to use this body array or CSV to array to convert what do you call that? CSV files into an array, but I don't really need this anymore, so I'm just going to delete this. So let's look for the frequency data. Okay, which is the column of frequencies that I want. Okay, I will have this peak frequencies.csv as the frequency array that I want to have. Okay, so remember frequency response data, I will have frequency, and then the complex number will be plotted at each of these frequencies. So the relevant frequencies here will no longer be this body array thing, but instead it will just be this peak frequencies CSV. So I'm going to copy this over, Control C, select and Control C, and I'm going to Control V here. Okay. Next thing, I will have the response also. Okay, it's no longer the body array. Okay, but the response will instead be the complex gain CSV. Okay. Well, it's not a CSV file, but it is it is this data file. Okay, originally I had it in CSV, but I won't put it. It's not. I won't convert it into CSV anymore. Okay, so I will have all of this being used. I'll take the sampling time. I'll take the frequencies, the vector of frequency and vector of responses, and then I will have a IDFRD object. So yeah, I'm going to do this. Convert it into IDFRD. Okay. So first thing I'm going to convert into IDFRD. So FR data equals to pick data to IDFRD. Okay. No more CSVs. So the pick data will be here, and then I'll just do that. So this is to convert everything into IDFRD data. Okay, so here's a list of functions. Okay, list of functions. Okay, so first I convert my frequency response data into an IDFRD object. So it seems to work well. Okay, so let's take a look at the frequency response data. Okay, sampling time is this. Okay, frequency, you have all of this over here, nicely plotted, and the response data is this. Okay, this is the response data. Okay, all the complex numbers are there, so that's fine. I'm going to close this. Okay, so that's okay. Alright, so next is I'm going to use TFS to generate a transfer function. Okay, so this is all what I'll be using. Okay, I'm going to copy and paste it here first. Okay, so next I'm going to use the TFS function. I stated previously. You can actually set your delay time, number of poles, number of zeros here. Okay, and then we'll get a transfer function system, and then lastly, plot transfer function versus data. How do I do this? Okay, this is what I have here is the manual way. What I have here is the automated way. So I'm just going to do body. Okay, transfer. Okay, maybe I'll do this first. I'll estimate the transfer function first based on the parameters given. Okay, so we have a transfer function. So I'm just going to do body transfer function. Okay, the function is called body because it's a body plot. So I'm going to compare two body plots. So where is it? Yeah. So let's see, body. So transfer function sys. So this is the estimated transfer function, and then next input will be the frequency response data, and the frequency response data I want to have it in stars. Okay, well let me do it this way first, then you'll see the result. Okay, so this is the body plot. Okay, you saw the Fourier transform very briefly. So you see, now you have two body plots here, the frequency and the phase. Of course, the phase thing looks a bit off, but I'll explain why later. You can see that this part actually matches very well, but you see the data is in lines, and then the transfer function is in a blue line. And as you look at the phase diagram, you may seem very that it doesn't match. But what you notice is that, you know, every time you have 0 degrees, it is the same phase as, let's say, 360 degrees. Okay, 360 degrees, the same units. Okay. Now, I mean, it's the same thing because 360 is one full revolution over. So when you have all this data here, you can subtract 360, and then you will see that the shape actually matches very well. Okay, one thing to note is that if you use body like that, use the body plot like that, the units are in radians per second, so you might want to change some things. Okay. So one way to do it is to change the units of the body plot. Okay, so I quickly show you where you can find it. Okay, we won't use the body function per se. We will use body plot. Okay. Okay, where do you find this? Okay. Okay, so normally, yeah, if you are okay with this graph, you can just use this body function, which will return the magnitude, the phase, and everything. But if you want to control control the output of your plots to make it look a little nicer, you use the body plot function. So let me demonstrate for you first how to use both of them. Okay, body is like this. You can use this body to actually return you frequency response data. But if all you're concerned with is the plot, then you can just type in like this. Okay, so body plot, and then it will literally return you your body plots. Okay, so the difference between body and body plot. Okay, difference between body and body plot. Okay, body gives you the frequency response data. Body plot gives you more options to plot your body plots. Okay, so that's all the difference there is. So body will give you all the frequency response data, even for the transfer function. Body plot is just, well, you can make it look nice. Yeah, you can make your stuff look nicer. So let's play with some of this body plot. Okay, one of the options, well, you can take a look here. To use body plot, you can actually put in multiple transfer function systems and multiple IDFRD data kind of thing. And all you need to do to change it is to change the plot options here. So let's go to plot options. Okay, or look at options. Okay. Okay, where's the phase matching? Yeah. Alright, so this is the example, one of these examples. Okay, so what we can do to do some of these options is as follows. Alright, never mind, this one looks a bit complicated, but okay. Let's do it this way, alright? Okay, we can actually have options like so. Okay, let me. Okay, so look at this part. Okay, you look at this part. Okay, so you type in this options equals to body options. So you can type that out in MATLAB. OPT equals to body options. Okay, so what's OPT? You see your units are now in radians per second. These are your defaults. Your frequency scale is in log. Mach units is in log. Mach scale is like linear, etc., etc., so on and so forth. Okay, so yeah, we can actually do something to change. We can change the units. Okay, so one of the options is the frequency units. So instead of radians per seconds, we can change to hertz. Okay, OPT dot. Okay, if you look here, you can see what things you want to change. OPT dot frequency units equals to hertz. So you can change it to hertz, and then we can do body plot transfer function system, and frequency response data, then you can load in your options here, and you look at what happens. Figure 1's here, and you can see all the frequency is now in hertz. So I'm going to put in like this, okay? OPT equals to bodeoptions, okay? And then OPT dot frequency units, right? We were changing the frequency units. OPT dot freq units equals hertz. So that's one of the data pieces in the object. So I did talk about this before. So we can put the options here, and we'll be using this syntax a lot when we want to change options of our plot, or even the transfer function estimation over here. But that one's for the next video. Okay, so we can change the units here. That's one thing. Next thing we can do is to change the what do you call that? I can change the plots. Okay, the orange curve, I want it to be stars. So let's change it to stars. So immediately after you put your frequency response data, just type this. Okay, it's a apostrophe asterisk apostrophe, and this will give you a star-like plot for your frequency response data. And let's take a look at our plot, and you can see it's a very nice cross. But of course, if you want orange, you can, well, I don't know, maybe you want to put it like that. I hope there's no syntax error. Okay, so maybe not. Yeah, that anyhow, yeah, I think it's good enough in terms of course, if you want a different colors and all that, you might want to use Excel instead of MATLAB to plot. It may be slightly easier, but yeah, this is what you can get. Yeah, so you can see the data actually matches very well with the frequency response fitted transfer function. Okay, so these are some basics on how to get your bode plot. And of course, if you want, yeah, I'm going to load. Yeah, next part you can load data. Okay, load data into arrays. Okay. So okay, maybe I'll do that in the next video because it's already 30 minutes. So thanks for watching. I'll see you again. Bye bye.